This is going to be on circles and forces at angles. And I'm just going to run through the free body diagrams and net force equations for the situations that I'm going to present and kind of talk about some side questions as we go. So the first type of question, or the most common type of forces at angles problem that gets asked, is something called a conical pendulum. So it's called a conical pendulum because it is something that swings back and forth in a circular pattern, and that object is going to trace out sort of a cone shape, hence conical cone pendulum swinging back and forth. So this conical pendulum is going to have a force of gravity and a tension force, and as shown on my diagram, we're usually given the angle that that tension or the string makes with vertical. So components wise, we should probably figure out what is our x direction and what's our y direction. So our x direction is going to be the direction of the circle, so nice and horizontal. And then our y direction is perpendicular to that. Now sometimes this can be really helpful if it's not immediately obvious what force needs to be broken up into components. So I'm seeing now that it's my tension force that needs to be broken up in components. So I have an Fty and an Ftx. Okay. In the y direction, my net force equation has to equal 0 because I'm not moving vertically at all. So my y component has to equal my force of gravity. In the x direction, that's the direction of our circle, so that's our centripetal force, and it's the x component of the tension creating that centripetal force. Now, one question that often comes up is, can the string ever be horizontal? So what horizontal means is that there's no tension in the y direction. So if we think about our drawing here, if there's no tension in the y direction, then there's nothing to balance with the force of gravity. And if there's nothing to balance with the force of gravity, then we must be accelerating downward. So it's actually impossible for us to swing this completely horizontally, okay? Because we always have to have some y component to balance with the force of gravity. Now let's chat quick about how to find those components. Okay. I have the angle with vertical, and the overall tension is my hypotenuse, which means that the x component is the side opposite of the angle, and the y component is the side adjacent. So that means the x component should use sine to find, the y component we should be using cosine to find. So Ftx ends up being Ft cosine. Nope, just kidding. Ft sine theta, right? Because sine is opposite over hypotenuse, and then I can cross multiply. And the y component is Ft cosine theta. So you have Ft cosine equals Fg. So tension is mg over cosine theta. Now this also helps to prove why the string can never be horizontal, because as the angle approaches 90 degrees, cosine of the angle approaches 0, which means I'm dividing by 0 in this equation, which in math means that that equation explodes. In the x direction, this mv squared over r would equal ft sine theta. So as the string becomes nearly vertical, right, meaning that the theta or the angle is approaching 0, right, the x component is then going to be approximately 0, which means we have to be moving with a very small radius and a very small velocity, because this is getting very close to 0 as we are approaching, because, whoops, as the angle approaches 0, the sine of the angle also approaches 0. So that means we have almost no x component, which means we have to be moving very slow at a very small radius. Okay. The other question that'll come up is this sort of like circle on an incline. So this is really common. You've probably played these games where you put a quarter down a ramp and it like spins around in a circle down this funnel. These questions are also asked as like cars on banked turns. Okay? They are asked first, usually without friction. Now, I will say that these question types, the next two I'm going to go over, are very uncommon on the APA exam. I've only seen them asked in the workbook, so if you don't want to watch the video anymore, you don't necessarily have to. Okay? But here, our free body diagram, and I'm going to do this, the object here, is going to look like a force of gravity and a normal force. Now, we are used to our x and y direction being like this. But if we're moving in a circle, those aren't the directions that we need to pay attention to, because those are not the directions we're accelerating in. Instead, we are accelerating horizontally in the direction of the circle, which then means our y direction needs to be vertical. Okay. So that means that the normal force is what needs to be broken up into components. Now, through some alternate interior angles, if this funnel side or bank turn is theta, then the normal force also makes a theta with horizontal, right? We got some like alternate interior angle action stuff going on. And I'm actually realizing that I labeled that wrong. This angle would be theta, which means this is 90 minus theta, because these have to create an angle like that. So here's where things get a little bit tricky. Right, so our normal force gets broken up into a force of gravity, a normal force in the y direction, and a normal force in the x direction. Now we have this angle here, 90 minus theta, or we could say that the angle that the normal force makes with vertical to make our lives easier is theta. Okay, and we saw before how when we have the angle with vertical, the x direction is really sine, and the y component is really cosine. Okay. So centripetal force, my Fn sine theta is going to equal mv squared over r. And in the y direction, we're going to have a net force of 0. So I'm going to have an Fn cosine theta has to equal force of gravity. So what this shows me is that my normal force actually has to be larger than the force of gravity, as the force of gravity is simply a component of the normal force. Unlike when I'm on an incline and I'm accelerating down the incline where my normal force is less than the force of gravity. Again, these questions don't really come up, so if you don't want to pay attention to that, that's totally fine. And I'm not going to go over the situation with friction because it just gets kind of complicated, and I don't want to confuse you anymore because you're not going to see that type of problem. So that is our final answer.